the sky have captivated us, particularly those special ones who mysteriously seem to wander. We call them planets, and upon learning that our planet is only one of many in our solar system, how can merely observing these points away from home ever have been enough? Half a century ago, we began the exploration of all the planets, making ever more distant journeys. Each new world, from Mercury to Neptune, revealed its own startling complexity, character, and unimagined beauty. As we now approach the Pluto system, reaching farther again, this year we are about to complete the historic first era of planetary exploration. Who knows what wonders await us at these new horizons.
So this was the New Horizons video from last year, and that's where the theme for our Astrigue New Horizons also comes from. So
Okay, sorry. So before Yu Jun continues, so all of you know that this is your third lecture. Then afterwards you will have your fourth lecture, and then you will be lunch time. So lunch will begin at about 12:15, and the facils will bring you to the canteen. So follow them, okay? And then for the facils, please collect the food for the participants. Participants don't collect the food yourselves. So facil, if there are 4 people in your group, then you just call them 5, 6, because 1 for you and 1 for 4 for them. Okay? Can? So participants don't collect the food yourselves. You'll be like very messy. So yeah. Enjoy the convention. Thank you.
only 2 more lectures, then lunch. Okay. So space exploration, okay, it can refer to 2 kinds of activities. The first is sending humans into space and getting them back. So this is what we call human spaceflight, and here is a stamp from Russia, and this is an astronaut. The space station behind is Mir, M-I-R, that's a Russian. The other kind of mission will be robotic exploration of the solar system, and just now New Horizons will fall under this category as well. So the photo here shows Mars rover, and as our friend just now suggested, the photograph in front of Mars was taken by this. This is the Falcon, and Curiosity is this one, the huge one, and we'll see how it actually grows, so it gets bigger over the years. So the video just now also explains the origins of the word planet. It means wanderer from Greek, and this is because when the ancient astronomers looked up into the sky, they realized that apart from the stars, which were generally fixed over the years, there were then other sorts of points that seemed to go back and forth, and which looked like they were lost, and so they gave it the name wanderer. So the question of celestial mechanics is, how do these planets move? And if we can understand how they move, then we also understand how we on Earth move within the solar system. So this gives us a sense of the cosmic scale of us humans being a very small part of the universe. And this sort of feeling is very common if you do space or astronomy. And this photograph is taken by Cassini spacecraft over Saturn, and this blue dot down here is Earth. So like literally our spacecraft is billions of miles away. Then they turned the spacecraft around, focused it in, and took a photo, and that's Earth. So all of our history of our people, everything is in that pale blue dot. And in the words of Carl Sagan. So okay, celestial mechanics then refers to the physics and math that is necessary for us to get there. And these can start from the basic physical laws like Kepler's laws and go to in the case of real actual mission planning, then physicists and engineers will have to use complicated software to calculate the trajectories and motion of these spacecraft. So interestingly, the word cosmos means order, and the opposite of this, cosmos, directly is chaos, which means disorder and just general lack of rules. So the reason that we give the word cosmos to the universe is because ancient astronomers believe that the rules that govern these celestial bodies can be understood by human exploration. So that's why for this topic, you see that space exploration is very closely related to celestial mechanics. Or in general, there are three key points for space exploration. First, it's difficult and very dangerous. Few nations have actually managed to go into orbit at all. And even the most successful ones, like Apollo mission by NASA, have a legacy of sometimes very difficult sacrifices as well. These three men here were the prime crew of Apollo 1. However, they perished in a fire in 1967 because of the rush to get to the moon. Some engineering decisions were made and it was quite faulty in hindsight. But you only realize that that was a mistake in hindsight. The original capsule was oxygen rich, so it was very prone to fire. And once the fire broke out, they couldn't be reached in time. Another reason why space is so dangerous is that you need a huge amount of energy to get into orbit. As we will see later on, there's a huge amount of energy needed to keep something in orbit around Earth. And the only way to get this energy is by a rocket. But the rocket is in itself basically a huge ball. So you're riding a ball to get into space. That's quite difficult. And lastly, if these astronauts want to get back in one piece, then they have to dissipate the energy in the bodies. So only after you dissipate it can you say use your parachutes and then slowly come back down to Earth. This photo shows a Soyuz capsule from Russia, and it's landing somewhere in Kazakhstan. So you have to dissipate the energy in part 2 in order to land and come home safely. Now we start by looking at the historical developments. This quote, "On the shoulders of giants," was by Isaac Newton, and it's very apt because Newton, together with other scientists, gave us a foundation of celestial mechanics as we know it, and allowed us to go all the way to things like Apollo and the lunar landings. So the first scientist we must look at is Johann Kepler. He gave us many observations of the stars and planets, and from his observations, he deduced the laws of planetary motion. So what's important is that what he did was empirical work. So as a scientist, he studied the world around him, and from the data, he got a certain law. It will be up to Isaac Newton later on to derive the theory of calculus and gravitation in order to prove that what Kepler did was physically sound. So Kepler sort of did an experiment in a way, then Newton gave him the theory and showed that mathematically his conclusions were sound. So let us first look at Kepler's three laws. His first law states that a planet orbiting the sun will move in an ellipse. An ellipse can be thought of as a stretched circle, and so it's fatter in the horizontally, and there will be 2 points called the focus points. What Kepler said was that the sun will be one of the focus points, and it will just move around in an ellipse. The second law states that if you connect a line between the planet and the sun, then this line will sweep out an area at equal rates. So say I have a planet X, if from January to February it moves this much, and then in September to October it moves this much, then these two areas must be the same, and that's the second law. The Kepler's third law states that the square of the period is proportional to the cube of the semi-major axis. The period is the time it takes to move one round around the ellipse, and the cube and the semi-major axis is half the distance, so it's from center to the edge. The whole thing is called the major axis, so you have the semi-major axis here. Then Newton derived the law of universal gravitation, and what this law states is that any two masses will attract one another with a force that's proportional to the masses of the two bodies and inversely proportional to the r squared. So if I have two bodies, I move them 2 times as far, then r increases to 2 times, and the force will decrease to 1/4 the original magnitude. And we can, using a constant g, we can calculate the force between the sun and the earth using the solar mass, or m1, and m2, the earth mass, and r will be the 1 AU. AU stands for astronomical unit, and it's this distance. So it's a distance between us and the sun. The term here, E13, means 10 to the power 30. It means exponent, so this is standard scientific notation. And once you calculate, we'll find that the force is about 10 to the power 22 newtons. So this may sound a huge lot, because like in ordinary life you don't quite meet these kind of big numbers. But in the case of astronomy, when we are looking at the motion of planets at such a huge distances, then these forces are quite normal, and it gives us a sense of scale, like how small our human world actually is. Then we now look at Kepler's first law. When Newton did the math of the gravitation law, he found out that any object orbiting a central mass will not just move in an ellipse, it will actually move in a conical section. And the conical sections are literally the sections you get where you cut up a cone, so conical. If I say I have 2 cones, they are 3D cones, and if I slice it horizontally, then I will get a circle. If my slicing is a bit slanted, then I might get an ellipse. So it's similar to a circle, but not equal in the radius. If I slice it even more slanted, then I will get a parabola. But if I slice it straight down, vertical, then I'll actually get a hyperbola. And these are the 4 conical sections. And why the trajectory is like that is a result of the 1 over r squared term in just now the equation of gravity. So to differentiate the 4 terms, so like as in how the 4 are unique, we must look at something called the eccentricity. This is the mathematical quantity. There's a ratio between the distance between the foci and the longest axis of the ellipse. So this is a definition. Let's look at actual ellipse to see how it works out. So here is the elliptical orbit in red, and the distance between the focus points or foci will be this bold line here. Then the major axis will be the distance covered by 2 arrows from furthest to nearest. And when we, from this diagram, can clearly see that for ellipse, this value will be less than 1 because this line is shorter than the major line. Then for the case of a circle, this value is actually 0 because the 2 points are not together and there's no focal distance at all. So for the case of a parabola, E is actually equals to 1. And the case of a parabola is called the escape trajectory, where the spacecraft or the planet, but some mass will go away to infinity. It will not come back. And that once it reaches infinity, there will be 0 velocity and energy at that point. Finally, we also have the hyperbolic object, which is even more energetic than the parabola. So from this diagram, you see the focal distance is here, and the major axis is here. So it's actually E greater than 1. So after we cover the theory, let's look at how gravity is actually applied to various space missions. So first we looked at Apollo 8. Apollo 8, now that it was actually a very, very dangerous decision by NASA leadership. So it was 1 year after the Apollo 1 catastrophe because the oxygen-rich environment, there was a fire, it killed the 3 astronauts, and they redesigned the whole capsule. Then at the same time, it was the first time they finished building a Saturn V rocket. So, of course, you have to test the system, make sure everything works. So, for the first test, what they're doing is basically propose to have a completely new spacecraft, a new rocket, and put people in it and go to the moon. And when they return to the Earth, hope that nothing burns up, like the heat shield, everything is okay. So, it was a very risky decision. But why they did it was there was a space race and they were in a hurry to beat the Russians. So, okay, then now we look at the photo. So, the diagram on the left, this is Earth, and the North Pole points out. So, this landmass here is the continental United States, and the launch site is Florida here. So, the Saturn V will launch up here, go into one parking orbit, and then it will head off towards the moon. So, the name here called free return is because when it goes to the moon, it will automatically come back by gravity. Like when you go here, there's now a repeated cycle to the moon. So in comparison to the dotted line, you don't have to switch on your engines and try to force an orbit back. You just follow the path and you naturally end up with a figure of eight shape. The wisdom of this is that in so doing, you don't have to like have a lot of engine burns along the way, and you have some sort of safety factor involved. And this will be validated later on by Apollo 13. So there's a movie, Apollo 13, starring Tom Hanks, and you'll see the trailer to give you a sense of what happened.
Apollo 13 flight controllers, give me a go, no go for launch.
You know that Easter vacation trip we had planned for Acapulco?
Procedures, go. Control, go flight.
There might be a slight change in destination. Maybe say the moon.
Booster, go. Retro,
We'll go flight.
GNC.
We'll go.
And I take the controls, and I steer it around. FAO.
We'll go fly.
For a nice, soft landing over the launch.
Does it bother you that the public regards this flight as routine?
There's nothing routine about flying to the moon. I can vouch for that.
Launch control, this is Houston. We are go for launch.
Houston, we have cleared the tower at 1313.
Hey guys, we're going to the moon.
Apollo 13, we should never go back on Earth. Pleasant evening. Houston, we have a problem.
We got a wicked ship here.
Houston, we are venting something out into space. It's definitely a gas of some sort.
Like the heart rates are skyrocketing.
The Apollo 13 spacecraft is apparently losing breathing oxygen. The emergency has ruled out any chance of a lunar landing.
Why are so many people here? Something broke on your daddy's spaceship.
I have a request from the news people.
Take it up with my husband. He'll be home on Friday.
Flight me, I've lost the radio contact.
Econ, what's your data telling you?
It's reading a quadruple failure. That can't happen. It's got to be instrumentation.
The ship's bleeding to death.
This rate, we're going to skip right out of the atmosphere, and we're never going to get back.
We're looking at less than 15 minutes of life support in the Odyssey.
We never lost an American in space. We're sure as hell not going to lose one on our watch.
Odyssey, do you read me?
How long does it take to power up the lamp?
3 hours by the checklist.
We don't have that much time.
That was Apollo 13. What happened on Apollo 13 was that it was supposed to be a routine mission to land on the moon and do some moonwalks there. But along the way, there was an explosion in the cryogenic oxygen tank. Cryogenic means very cold. So the oxygen tank was sort of liquid state. So oxygen was liquid state, and there was a wiring issue. So there was a spark, and that caused the explosion. So immediately after the explosion, the crew started losing oxygen, and this also led to a reduced power supply. So now they are going short on life support, and power is also down. Then there's no way they can land on the moon. Even getting back to Earth will be a challenge. So down here you can see how the lunar free return works. All they have to do is keep on going to the moon and go behind the moon, and they'll naturally come back. But of course, this will be a leap of faith, because when they are behind the moon, all contact will be lost between the spacecraft and mission control in Houston. So the people here know that their spacecraft is damaged and 3 lives are at risk. But for a period of about an hour or so, you are out of contact. You can't communicate with them at all because the moon is in the way. Also, the famous story about how you fit a round tube into a square hole was because of the oxygen running low and the carbon dioxide content was building up. So they had to sort of have more carbon dioxide scrubbers, but then they are not designed to match. So what the astronauts did was, under the command of the people on the ground, they used a lot of duct tape to just force the two together. So that's the origin of this term. And of course, Apollo 13 returned safely to Earth, and the mission controller, just now the guy with the crew card, yeah, that's him jumping in the air. So now we go and look at Kepler's second law. Second law states that the line joining the two bodies will sweep out the same area in an equal time. And this means that the satellite will move faster when it's closer to the sun or closer to the Earth than when it's further away. So down here, from A to B will be faster than from C to D. And this is a result of the conservation of angular momentum. Angular momentum is a physical quantity. It's like when someone is skating on ice and they pull their hands together, then they will spin faster. So this quantity is conserved in space because there's no friction or no air during that motion. Okay, then Kepler's third law states that T squared is proportional to A cubed. And Kepler actually empirically found it. We can of course use it for using what Newton gave us, using calculus and gravity for the elliptical shapes as well, but for simplicity we'll look at a circular orbit. The gravitational force allows the satellite to move in a circle. So we have the centripetal acceleration here. Omega is the angular velocity, which we can write as 2 pi radians over the period t. And when we expand the square, we'll get this expression, giving us r cubed and t squared. Note that if we use the units of astronomical unit for r and years for t, then these two will give us exactly 1. So r cubed is equal to t squared if this is in AU and this is in years. So not SI units, but if we change the units, then the GM term is unnecessary. And note that for the hyperbola and parabola, the t is meaningless because it will not contact. So this is generally only for the elliptical orbits or the circular orbits. Now we consider a thought experiment where I have a very, very high mountain and a cannon on top. So I can fire out cannonballs at different velocities. If the speed is too low, then from common experience, we know it will just fall back to Earth. But some of these falling back will take the form of ellipses as well. And I can increase the velocity until I go into orbit, and that will be the orbital velocity. So if I go beyond the orbital velocity is the minimum one needed to move in the circle. If I increase that, I'll get ellipses all the way until I hit something called escape velocity. So you can imagine the circle getting stretched, all the way until a parabola where it doesn't even come back. So to hit the parabola, that's why we call it the escape velocity from just now. And so the escape trajectory and the velocity here is escape velocity. If you increase the speed, you increase the energy beyond the escape velocity, then you end up with a hyperbola. And so the parabola is at the boundary between the ellipses and the hyperbolas. To work on the orbital velocity, we also consider the gravitational force and the centripetal acceleration. Except just now we use omega, now we don't write in terms of omega, we write in terms of the velocity. And equating those two forces, we get this expression. Note that it's independent of the satellite mass, so a big satellite and small satellite will all have the same orbital velocity. And it depends on where your satellite is in terms of the altitude. Also, just on the point number 12, the huge amounts of energy needed, it's precisely because of this. From the stationary rocket or stationary plus rotating Earth, you have to move into an orbiting orbit, and that takes a huge amount of energy, and that's why you have to use rockets. Now, the first object to enter orbit was Sputnik, launched by the Soviet Union in 1957. It's something like a radio transmitter in space, going deep all over the world, so that internationally everyone knows how awesome the Soviet Union is. Then the other velocity just now we saw was escape velocity. It's very similar to the orbital velocity, except now there's a square root 2 as well. So to derive this, we need to go back to the definition of escape velocity, where the energy at infinity, it will move to infinity, but the v will go to 0. So these two terms must be equals. And we add up these equals to 0, and when we move the half over, then we get the orbital, we get escape velocity. The first object to gain escape velocity, or manning object, was Luna, launched in 1959 by the Soviet Union as well. So from the name, you recognize that this is a moon probe. And to go to the moon, of course, you must escape from Earth's orbit, and that's why it will hit the escape velocity. But I probably move in a hyperbolic orbit. Like, because the parabolic orbit is just nice to get the velocity. So it's a boundary, and it's quite, like you have to, if you are only a little bit beyond this, technically you'll start moving in a hyperbolic. Okay, this is just for fun, and those of you who know some history might have heard of the term Cold War, and the space race was part of it. So the rocket that launched Yuri Gagarin into space was a modified intercontinental ballistic missile, the Soviet Semyonov R-7. So this is the weaponized version, this is the one with him on top. Also, Werner von Braun, the German behind the American space efforts, started out under Hitler's regime building the V2 Wunderwaffe. So this is also a military missile, and you see how the same technology can apply both ways. Of course, at the same time, space will also bring out the best in humanity. And just now, one of you suggested Curiosity, and this is a photo that Curiosity took also on the Mars. So it's the same sun and the same color and all that. So it's very beautiful how we can actually get this image now. And this photo shows the moon eclipsing the Earth. So very nice. Now we look at some of the current programs, and here is the Expanding Horizon. It's quite an active one. That spacecraft there is the Hubble Space Telescope. We must of course mention the Space Shuttle. It was a partially reusable spacecraft by the US, and some of its greatest achievements was the assembly of the International Space Station and also the maintenance of Hubble Space Telescope. The International Space Station consists of many small little modules and things like trusses, solar panels, crew modules, etc. So what the Space Shuttle did was it brought the module into space and assembled it by the astronauts doing spacewalks in orbit. Why this is so helpful is because if you don't use a space shuttle, like the Russians, then you have to make your module have some form of propulsion. And this increases the risk very exponentially because now you're putting some funny chemicals beside what humans are supposed to stay inside and launching into orbit. So in comparison to this, the space shuttle allowed for a very efficient design of the space station. And the other aspect is Hubble Space Telescope. It was designed from the start to be able to be serviced by astronauts. So what Space Shuttle would do would be it flies beside the Hubble Space Telescope, grabs it with its arm, and also allows spacewalks. So that is how the lifetime of Hubble was extended and the optics was upgraded. So all your beautiful pictures like the pillars of creation, those were only made possible thanks to the Space Shuttle and the continuous upgrading until 2011. The other spacecraft to know is Cassini-Huygens. So Cassini is very big unmanned spacecraft, and it was launched in the 90s. So back then the technology was already so advanced. It was powered by a radioisotope thermoelectric generator. It basically means some form of nuclear propulsion, but of course they will never use the word nuclear to the public. And the photograph that we find showing Earth inside the ring sources was taken by Cassini. So this gave us all these stunning and beautiful images from the outer solar system. Now the Huygens part of Cassini-Huygens. Sorry, one more thing is the trajectory. What it did was gravity slingshots because our rockets have a limited amount of energy. And the further you go, the more energy you need to expand. So rather than have a huge rocket, because that will exponentially increase the engineering complexities, they just fly past the planets. And like it's something like a slingshot. You go in slow, but once you get into orbit, they will shoot you out at a very fast rate. So that's what happened when it passed Venus, passed Earth, then Jupiter, then finally it reaches the target destination. This motion is of course not free. It does follow the laws of conservation of momentum and all that. Okay, now for the Huygens part of Cassini-Huygens. Huygens was a lander that was targeted at Titan, one of the moons, and this was an actual photograph that returned on the moon itself. So you see how barren and how alien this landscape is. The technology they used was basically a parachute to slow down and touch down on solid rock. Okay, so we now turn our attention to somewhere closer to home and more readily accessible to humans. That is Mars. This is NASA's Mars exploration pathway. And you see, okay, firstly, they want to commercialize low Earth orbit so that they can turn their attention to space exploration at Mars. And the rocket that they are always promoting, the Space Launch System, fits in here, together with the Orion Spacecraft here. What we already have will be the landers and the rovers, and also some orbiters. So orbiters is like satellite orbiting Mars. They give us photographs and allow us to choose potential landing spots. So now that we want to get to Mars, we also have to use celestial mechanics, and this is called the Hormone Transfer. The Hormone Transfer is the fastest way to get between one orbit to another orbit by making use of this half ellipse in between. So I'm in orbit 1, I want to go to 2, I do this, and this orbit, of course, is also determined by the mass of the sun inside. And to calculate the time needed, all we need is to know the semi-major axis of orbit number 2 and use Kepler's third law. So this major axis is the semi-major axis of 1 plus that of number 2. Plus that of number 3, and we divide by 2, and so we add this plus the 1 AU divided by 2 and plug it in, and we will get a value of about 8.5 months. So what this means is, if I launch, say, Sojourner in 1997, I have to wait 8.5 months for it to reach Mars. And so you have to plan very much in advance and make sure that all your systems are functional. In addition to that, you literally have to wait for the stars to align, because this sort of alignment occurs only every 2.5 years. The orbital rates of Earth and Mars are different, so you have to wait until they align periodically. So that's why all the NASA missions are like every 2+ years, then it repeats. That's what's the optimal window. For, say, launches to the moon, that window is about a month or so, and it occurs quite frequently. So you don't have to wait 1+ years, because the moon is closer to Earth, and you don't have to have such a big scale maneuver. Okay, so now we look at some of the rovers that NASA has already sent to Mars. The first is Pathfinder Sojourner, which took the photograph earlier on, and there was a camera like this in the movie The Martian, where Mark Watney uses Sojourner to establish communication with Earth. So yes, this part is real. the spacecraft exists. JPL stands for Jet Propulsion Laboratory. It's a branch of NASA that does all these Mars explorations. So we fast forward 6 years to Opportunity, and we see how the rover program has grown. You see the suspension systems, bigger wheels, bigger surface area for the solar panels. Because Sojourner is so small, like a small area is enough, but for spirits you need a bigger area. Then finally, the most recent one is Mars Science Laboratory, also known as Curiosity. And in this case, the spacecraft actually draws the human. It's about the size of a family car. And it's also powered by a radioisotope generator in here. So there's something nuclear out there as well. Okay, now we move on to some of the future developments. And this title might sound very esoteric and clear to you, not space related. But Berlin actually is the name of the engine of the SpaceX Falcon 9. So there are 10? No. There are 8 Berlin engines because Mars. There are no oceans on Mars. There are no landways. There are no landing pads or airports, and there's definitely no Kazakhstan grass field for you to land on. The only way you can get any big amount of mass is just by propulsive descent. You have to fire your engines and land straight, because otherwise you're not going to land at all. And this quote, because nobody wants to go back to Jakku, was said by one of the SpaceX engineers during the December launch last year. So anyone recognize where Jakku is from? Yeah, that was December. So to show that you watch TV does not have a life. Okay, just now we mentioned that the space shuttle was partially reusable. And what SpaceX wants to do is a fully reusable system. This will allow the costs to be dropped dramatically. Like, imagine I have a 747. If I throw the plane away from every flight from New York to London, then only the billionaires can fly. Everyone else cannot afford a ticket. And we look at Saturn V, the moon rocket. Only this tiny part in front lands and comes back to Earth. Everything else is just thrown away in the ocean or left in orbit as just more orbital junk. So what SpaceX is doing is game-changing completely. And in order to have a greater flexibility of landing, they are trying to land on a drone ship. The mission will lift off, get the satellite in orbit as usual, but then after the satellite separates, like after the top goes off, the first stage will come back in and rotate, and then we'll sort of try to stick a landing on the autonomous drone ship. We'll go into detail of what that means later on. So there are 3 key features that enable this engineering to work. first is the descent. It's a descent burn. The engines have to be able to be reignited, and that's why Merlin is so awesome at this. The second part is aerodynamic guidance, because we want to guide this rocket. But you have a limited amount of mass, you can't always fire engines. You need something like wings. And lastly, you want to have a vertical landing. So you want to have a platform, a system where you can land such a, like a pencil on the teeth of an eraser, something like that. So we now look at what Falcon 9 is so special. Elon Musk calls these features the X-fins. They are grid fins. And why SpaceX uses grid fins is because they work well at a range of velocities. When the rocket is coming in above the speed of sound and even below the speed of sound, the fins will work very nicely throughout. If they had used wings, then the wings will have a very narrow range. If you go beyond this speed or lower than this speed, then it won't work at all. Whereas grid fins will allow them to maintain control throughout the descent. The second aspect is the landing legs. So the protrusions that you see here are landing legs, and they will unfold and allow the rocket to land once it's close to the drone ship or the landing pad. Lastly, for finer minute adjustments, they use the attitude control system. Attitude means orientation. So they are firing nitrogen gas out, and this will give them a moment of force, and will allow them to rectify this and go straight down. If the rocket comes in at an angle, they will topple over and they won't be able to nail the landing. Apart from the Falcon first stage, the other innovation they are pursuing is the Super Draco engines. The Super Draco will be mounted on the Dragon spacecraft, and this will allow the spacecraft itself to land vertically. It will be like all those 1950s superhero films that, okay, your rocket goes up and comes back down straight. But this is modern science. And another vital aspect is that the Super Dracos allow the spacecraft to have abort capability, which means, say I have a Falcon 9 launch. If something goes wrong in the Falcon 9, my astronauts and my Dragon must be able to detach and fly off to safety. So that's called the abort capability, and that's what the Super Draco engines will offer. Now we can contrast this engineering approach to what NASA is doing later on. So last year, December 22nd, was the first landing of the Falcon 9 spacecraft. It was the first operational first stage landing. So what this means is, it's real. Like, this was a rocket that went into orbit and came back down. Some of you may have heard of Blue Origin and what they are trying to do with the VE4. Actually, those missions are less challenging than what SpaceX is doing, and their rocket is much smaller than something a Falcon 9 this size. So this is the actual rocket that landed on dry land. And what you will see is that there's an interesting section of white in the middle. This is because this middle section is the cryogenic liquid oxygen tank. So cryogenic oxygen, you first encountered it just now in Apollo 13 slides. So it's cryogenic because the density increases, you can pack more oxygen for the same volume. And because it's so cold, there will be condensation around the rocket core, and as it comes back down, the heat will vaporize the water instead of giving us a soup pattern around here. So yeah, the bottom and the top have a bit of soup, of course. And now let's watch this video, the landing.
BC, start the launch sequence. Clock, we're ready for engine chill in 30 seconds.
Prompt is ready for engine chill. Stage 1 pods, stage 1 fuel, stage 2 filaments on.
All stations verified, ready for launch. All stations are now FTS.
And we can hear.
Maybe I
They tend to refurbish this booster and fly it sometime afterwards. Okay, so this is breaking news. So before this, that landing was on ground, okay, on some, I think the Cape Canaveral, so somewhere in Florida. But as part of the plan, they wanted to land on a drone ship, because if you have a drone ship, then you don't have to fly all the way back here. You just fly a little bit to your ship. So it's like, it will be necessary in the long term. But this is a lot more difficult because your ship in the ocean is going up and down in ways that your area is also smaller, so it's more difficult. Then they failed so far all the way before December 22nd, and earlier on this year as well, it was also a failure. It was so close. But this is breaking news. They managed to nail a drone ship landing this morning, just now about 4-5 a.m. Singapore time. They landed on the drone ship. This is in the middle of the sea, and you see it coming down. Like, just now. And of course, there are these two patterns here forming. Like, okay, so that's SpaceX. Okay, let me see what NASA is doing. Just now for point number 3, about the huge amounts of energy, you have to dissipate that energy. And NASA has this thing called hypersonic inflatable aerodynamic satellite. It's a very long name. But you can think of it as a big balloon that will inflate to be like an umbrella. If you have ever tried holding an umbrella in front of a wall, you will find that it's a lot more difficult because there's air resistance. And that's precisely what they want to do on Mars by using this atmospheric resistance to slow down your spacecraft. When you're coming in via the Hormone Transfer orbit, you have a huge amount of energy and you must dissipate it. So why it's called inflatable is it's like a balloon. Initially very small, so the volume is small. Then I inflate it like a car airbag, and suddenly I get this huge aero shell as well. Then there's this Orion flight test. That is not Orion, but it looks visually similar. So thank you. This is Orion. It landed in the ocean, and so this is like very Apollo-ish, very heritage designs. It's not really groundbreaking anyways. And the big problem is, if you see the ship of Space One system, SLS progress, there's like a needle thing pointing out at the top. That is NASA's version of the launch abort system, this thing. So if all goes well, LAS launch abort will be just thrown away in space. But this of course makes the whole thing look like a wasted mass, which is, like you have to spend so much fuel just to get this piece of mass into orbit and then you're throwing it away. What a waste. And this is legitimately 1960s technology from the Apollo days. Apollo also used this kind of tech, now they're doing. And what's the worst part is, it increases the complexity because now you have one more event, you have to break the shell, you have to throw it away. So you contrast this kind of design with what SpaceX is doing with the Super Draco. The Super Dracos are inbuilt to Dragon, so there's no need for any sort of separation event. And the Super Dracos also allow it to have a landing capability. So this is innovation, right? This is what a legit 21st century spaceship will look like. Don't know about this. Okay, so in conclusion, in just about 300 years, we have come from Galileo to Newton to von Braun. And in terms of spacecraft, we have built from like this bamboo chair to Soyuz to Space Shuttle. And the question is, where will we go next? Okay, so just now that I mentioned, the last Space Shuttle mission was STS-135, and the Commander Ferguson had this quote: "They are not ending the journey. They are only completing a chapter of a journey that will never end. And perhaps one day we will see this on us." Thank you.